Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Have you ever considered the inherent bias in how we observe the universe?
It's a massive bias.
Right. I mean, when you look up at the night sky, you are basically experiencing a severely filtered version of reality.
Just a tiny fraction of what's out there.
Exactly. You see the stars, the planets, maybe the Andromeda galaxy if you are in a dark enough location.
You're lucky.
Yeah, if you're lucky. But fundamentally, human eyes, and by extension, the vast majority of our optical telescopes, they are drawn exclusively to the brightest sources of light.
It's a foundational paradox in astrophysics, really.
It is. We build our entire models of the cosmos based on these blazing beacons in the dark. You know, the massive, highly luminous galaxies and quasars.
But doing that, relying just on the bright spots, leaves a monumental blind spot.
A huge one. Because what about the vast spaces between those objects? Seemingly empty voids. Because they are not empty at all.
Far from it.
So today we are doing a deep dive into a groundbreaking publication from the Astrophysical Journal. This was released very recently, March 3, 2026.
Based on some incredible data.
Yes, data from the Hobby-Eberly Telescope Dark Energy Experiment, which we'll refer to as H-Edectics. Our mission today for you, the listener, is to understand how astronomers are finally looking past those bright stars.
They're finding a hidden ocean, basically.
A vast hidden sea of light residing right between early galaxies. And we'll explore what mapping this invisible cosmic web actually means for our fundamental understanding of the universe.
This research really represents a complete paradigm shift in observational cosmology.
How so?
Well, we are looking at a highly critical epoch in the universe's history, specifically the period between 9 and 11 billion years ago.
Okay, let's unpack this. Why are astronomers so heavily focused on this particular window? What makes the universe of 10 billion years ago so crucial for understanding the galaxies we see around us today?
That time frame, it corresponds to what astrophysicists often call cosmic noon.
Cosmic noon, I love that term.
It's very descriptive if you look at the cosmic star formation rate history.
Which isn't a flat line, right?
Not at all. The universe did not produce stars at a constant rate. About 9 to 11 billion years ago, the universe was experiencing its absolute peak of star formation.
So it was just churning out stars.
It was an incredibly dynamic, violently active epoch. The galaxies during this period, they weren't the settled, beautiful spiral galaxies we see today.
Like the Milky Way.
Right. They weren't like the Milky Way. They were chaotic. They were actively pulling in or accreting massive amounts of primordial gas from the intergalactic medium.
Just feeding on this gas.
Exactly. And igniting stars at rates hundreds or sometimes thousands of times higher than what our galaxy does today.
So it's essentially the peak of cosmic construction. But observing that construction comes with significant physical limitations, doesn't it?
Very significant. The primary limitation is just surface brightness.
Because it's so far away.
Right, because we're looking at objects 9 to 11 billion light years away. The inverse square law dictates that the light reaching us is exceptionally faint.
Okay, but we can see some galaxies from back then.
We can resolve the most massive, hyperluminous galaxies from that era, yes. Because their localized starburst activity is so incredibly intense.
But the smaller stuff.
The fainter dwarf galaxies, and more importantly, the sprawling filaments of diffuse hydrogen gas that form the cosmic web.
The fuel lines, basically.
Right, the fuel lines. They fall well below the detection limits of standard optical imaging. The light from that diffuse gas has spread out over billions of light years.
By the time it hits a telescope mirror on Earth,
it's effectively indistinguishable from the ambient background noise of the night sky, or even the thermal noise of the camera instruments themselves.
The time machine aspect of this is something that always strikes me. We use that term colloquially, but mathematically, that is exactly what telescope data from this era represents.
It's literally a time machine.
Right, because the speed of light is a hard limit. When we pull data from H-Edectics that originated 10 billion years ago, we are capturing photons that have been traveling through the vacuum of space since before our sun even existed.
Long before. The Earth is roughly 4.5 billion years old.
So this light had already been traveling for over 5 billion years before our planet even coalesced from a cloud of dust.
It's staggering to think about.
It really is, and capturing that specific ancient light to reconstruct those early fuel lines, it requires an entirely different approach than just taking a long exposure photograph, right?
You get to take a picture. Taking a standard optical image of this epoch to find diffuse gas is largely futile.
Because the background washes it out.
Exactly. The broadband filters used in standard photography or photometry simply let in too much background light. It washes out any faint structures.
So what's the alternative?
To map the intergalactic gas 10 billion years ago, we have to abandon images completely. We rely almost entirely on spectroscopy.
We're not looking for the physical shape of a galaxy anymore.
No, we are looking for the highly specific physical signatures hidden within the electromagnetic radiation itself. We isolate distinct wavelengths of light that prove the presence of specific matter.
That requires transitioning our focus to the actual language of light, the spectrum. Now, for you listening, breaking light down into a spectrum reveals the emission and absorption lines of chemical elements.
Like a cosmic barcode.
Right, a barcode. But I want to zero in on the specific wavelength that makes this entire HEDEX map possible, the Lyman alpha emission line.
The holy grail for this era.
Why is this specific quantum transition the ultimate tool for looking at the cosmic noon?
Well, the Lyman alpha line is the cornerstone of high redshift observational astronomy. To understand why, we just need a quick look at the quantum mechanics of the hydrogen atom.
Which is the most abundant element out there.
By far.
Yeah.
So when a hydrogen atom sits near a region of intense star formation, like those massive chaotic galaxies we talked about, it gets bombarded by extreme ultraviolet radiation.
From the young, hot stars.
Yes, specifically massive O and B type stars. This radiation is so energetic that it ionizes the hydrogen. It physically strips the electron away from the proton.
And the signal we are looking for is created when that electron finds its way back, right?
Correct. When the proton eventually recombines with an electron, that electron cascades down through the atom's specific quantized energy level.
It's like stepping down a ladder.
Exactly like stepping down a ladder. And when it drops from the first excited state down to the ground, the bottom rung of the ladder, it releases a photon with a very specific, unchangeable wavelength.
And that wavelength is?
121.6 nanometers. That is the Lyman alpha line.
121.6.
Okay. Because the early universe was absolutely dominated by hydrogen and the star formation rates were so extreme, these galaxies act as colossal Lyman alpha factories. They pump out an astonishing number of these specific photons.
But wait, 121.6 nanometers is deep in the ultraviolet spectrum. That's invisible to the human eye.
It is.
And it doesn't stay at 121.6 nanometers either because of the expansion of the universe.
Right, the redshift.
As those photons travel through space for 10 billion years, space itself expands. It physically stretches the light waves.
So by the time they reach the HET-X instruments in Texas, that ultraviolet light has been redshifted straight into the visible optical bands.
Right around 350 to 550 nanometers, greenish-blue light.
Exactly.
The source material notes this shows up as a dramatic peak in the data. If you picture the spectrographic feed, you have this relatively flat continuum of background emission, and then boom, a violent, unmistakable spike.
At that specific redshifted wavelength.
It's the undeniable fingerprint of excited hydrogen at that exact distance in the universe.
We call that dramatic peak a Lyman alpha emitter, or an LAE.
An LAE?
Finding those massive spikes is the traditional methodology for locating high redshift galaxies. If you see that peak, you have definitively located a bright, active galaxy from that specific epoch.
But the galaxies aren't the whole story.
No. Theoretical models of the cosmic web have always suggested that Lyman alpha emission shouldn't just be restricted to the massive galaxies.
The gas in between them should be glowing too.
The vast filaments of intergalactic gas drifting between the galaxies should also be emitting these photons, either through recombination from the background radiation or just from gas falling into dark matter halos and heating up.
But the emission from those gas filaments, that would be orders of magnitude weaker than the galaxies themselves.
Vastly weaker. I mean, the peaks from the galaxies are highly localized. They're relatively easy to extract from the data.
They stand out.
They do. But the emission from the intergalactic gas is exceptionally diffuse. It's just a subtle, incredibly faint glow spread across massive cosmic volumes.
And for decades, finding that faint signal was thought to be impossible.
Virtually impossible on a large scale. The instrumental noise, the foreground light from our own solar system, it all drowns it out.
Which brings us to the sheer scale of the instrument required to even attempt this. You cannot just point a standard observatory telescope at the sky and hope to map this stuff.
No, you need a behemoth.
You need the Hobby-Eberly Telescope Dark Energy Experiment at the McDonald Observatory in West Texas. Let's discuss the volume of this survey, because the engineering reality of HET-DEX is staggering.
The Hobby-Eberly Telescope, the HET, is a totally unique piece of engineering.
Most big telescopes move on dual axes, right? They tilt up and down and spin around to track the sky.
Right. But the HET has a fixed elevation angle. It sits permanently at 55 degrees.
Okay.
It simply rotates in azimuth, around in a circle, while a highly complex tracker moves across the focal plane at the top to follow the astronomical targets as the Earth turns.
That's incredibly clever.
It's very efficient. And for the dark energy experiment, the telescope was upgraded with a massive array of spectrographs. They call it VIRUS.
The Visible Integral Field Replicable Unit Spectrograph.
That's the one. And VIRUS isn't just one single instrument.
No, it's a massive replication strategy. Instead of building one giant spectrograph, they built dozens of identical units and fed them with thousands of optical fibers.
Over 30,000 optical fibers.
30,000.
This allows HE-DEX to perform integral field spectroscopy on an industrial scale.
Yeah.
They're taking spectra of thousands of discrete points on the sky simultaneously.
And their primary mission, as the name implies, is mapping the expansion history of the universe to constrain dark energy.
Yes. Their stated goal was to chart the 3D positions of over 1 million bright Lyman alpha-emitting galaxies.
To get that catalog of 1 million galaxies, they had to cover a massive area of the sky, an area measuring over 2,000 full moons.
It's a huge swath of the celestial sphere.
Let's help you visualize that. The angular diameter of the full moon is about half a degree. So taking up 2,000 full moons, that is a massive, sweeping expanse of space.
They're just blindly pointing these 30,000 fibers at the sky, pulling in light, separating it to wavelengths, and generating an unbelievable 600 million individual spectra.
Here's where it gets really interesting. Carl Gebhardt, the principal investigator for @DenX, revealed a metric about this data collection that fundamentally alters how we view these surveys.
It really does.
Despite gathering 600 million spectra, that primary dark energy mission, the effort to map the 1 million bright galaxies, it only utilizes roughly 5% of the collected data.
5%. That is the crucial pivot point of this entire deep dive.
It's wild.
The primary pipeline for HDEX is designed for point source extraction. It scans all 600 million spectra, looking for high signal-to-noise ratio peaks.
The bright galaxies.
Exactly. Once it identifies and catalogs a galaxy, the rest of the data surrounding that peak, which makes up 95% of the total data set, is mathematically categorized as background noise.
They threw out 95% of the data. I mean, not literally deleted it from the hard drives, but scientifically it was sidelined.
It was ignored.
You build this incredibly complex array of 30,000 optical fibers, you survey 2,000 full moons of sky, and 95% of the photons you catch are deemed irrelevant just because they don't cross a specific brightness threshold.
Well, from a traditional survey perspective, that is standard operating procedure.
Really?
Yes. If your objective is a highly pure catalog of discrete individual objects, anything that cannot be confidently resolved as an object is an impediment.
It's just getting in the way.
Exactly. It's foreground light, it's atmospheric air glow, it's thermal noise in the CCD detectors.
But Masha Luja-Niemeyer and the team behind this new publication, they recognized a profound philosophical flaw in that approach.
They realized that 95% is not empty noise.
No. Among the instrument artifacts and the airglow is the literal sea of light from the cosmic web.
It contains the aggregate Lyman alpha emissions of all the dwarf galaxies that were too faint to trigger the detection algorithms, plus the glowing filaments of intergalactic gas.
It's the difference between mapping the peaks of a mountain range and mapping the entire tectonic plate underneath it.
That's a great way to put it.
The bright galaxies are just the most luminous nodes of a much larger interconnected structure. But the challenge wasn't getting the data HEADX already banked half a petabyte of it. The challenge was statistical.
Highly statistical.
How do you extract an incredibly faint, highly diffuse signal from a data set where the noise is orders of magnitude louder than the signal?
You have to completely abandon the concept of object resolution.
You stop looking for individual things.
Exactly. You can no longer ask the data pipeline to find a specific galaxy. This requires transitioning to a technique known as line intensity mapping.
Line intensity mapping, or LIM.
LIM fundamentally redefines the objective of the survey. Instead of searching for spatial coordinates of bright peaks, LIM measures the integrated surface brightness of a specific spectral line across large cosmic volumes.
To make that concrete for you listening, Julian Munoz, a co-author on the paper, offered an excellent analogy regarding how we view the spatial distribution of light.
The airplane analogy.
Yes. He compared the traditional cataloging method to flying in an airplane at night and trying to map a country's population by only looking at the brightest city centers.
It's highly illustrative. If your optical sensor on the aircraft is calibrated to only register the intense light output of major metropolitan areas like New York, Chicago, Los Angeles,
then your resulting map implies a binary distribution.
Exactly. It implies there are intense points of existence surrounded by total empty voids.
But we know demographically that the population is continuous.
There are sprawling suburbs, rural highway corridors, and small towns connecting those major hubs.
And the traditional point source extraction of ATX was mapping the cosmic cities, but it was completely blind to the cosmic suburbs and the interstate highways of gas connecting them.
Because the light from the suburbs isn't concentrated enough to trigger the sensor.
So to map the entire landscape, Munoz suggests keeping the airplane at the exact same altitude, looking at the exact same landscape, but changing the optical properties of the sensor.
You look through a deliberately smudged window.
A smudged window.
The smudged window represents the spatial and spectral smoothing inherent in line intensity mapping. When you apply a smoothing kernel to the data, you intentionally degrade the resolution.
You make it blurry.
You make it very blurry. You can no longer distinguish the sharp boundaries of the major cities. The points of light blur and expand.
But there's a mathematical advantage to that, right?
A critical one. While resolution is lost, the total photon count is conserved. It's aggregated. The faint, sub-threshold light from the cosmic suburbs is integrated into larger volumetric pixels, which we call voxels.
Voxels, 3D pixels.
Right. And by integrating over larger volumes, the faint signal of the diffuse Lyman alpha emission constructively interferes. It naturally rises above the threshold of the random, uncorrelated instrumental noise.
It's a brilliant statistical maneuver. You sacrifice the ability to say there is a distinct dwarf galaxy exactly at coordinate X.
Right.
But you gain the ability to say this entire region of space is radiating a faint Lyman alpha glow. The blurry picture actually contains more cosmological information about the distribution of matter than the sharp, highly filtered picture did.
It's a more complete truth. Now, the source material does clarify that line intensity mapping itself is not a newly invented concept.
Right. Radio astronomers have used it.
They've used it for years to map the 21-centimeter line of neutral hydrogen.
Yeah.
But applying this technique to the ultraviolet Lyman alpha emissions in the optical band,
over a survey area of 2,000 full moons.
that is entirely unprecedented.
And the application at this scale introduces formidable computational complexities.
Massive complexities. In 21-centimeter mapping, the foregrounds are intense, but the spectral line itself is relatively straightforward.
But Lyman alpha is messy.
It's a resonant line. The photons scatter repeatedly off neutral hydrogen atoms before they ever escape the galactic halo. It makes the radiative transfer extremely complex to model.
Plus, the data set itself is gargantuan. To apply line intensity mapping to the discarded 95% of the HZX data required processing roughly half a petabyte of raw spectroscopic files.
Half a petabyte.
Let's give that some scale. If you consider a high-definition movie to be roughly 5 gigabytes, half a petabyte is equivalent to 100,000 high-definition movies.
You're not doing that on a laptop.
No. Processing that volume of data isn't something you do on a workstation in a university lab. The team had to rely on the Texas Advanced Computing Center, or TACC.
They were utilizing supercomputers like Frontera and Stampede.
Running completely custom pipelines. They had to mathematically strip away the atmospheric emission lines, the foreground zodiacal light from our solar system, the galactic cirrus from the Milky Way, and all the instrumental artifacts.
From 600 million spectra.
All without accidentally erasing the incredibly fragile, ultra-faint Lyman alpha signal hidden underneath.
The data reduction pipeline is an engineering marvel in itself. But raw computational power is meaningless without a rigorous physical framework to guide it.
Right.
If we connect this to the bigger picture, the actual methodology used to reveal the cosmic web relies on a foundational property of cosmology.
Gravitational clustering.
Exactly. The universe is not a uniform soup of matter. It is heavily structured by the gravitational potential wells of dark matter halos.
And this is where Eiichiro Komatsu's signpost technique comes into play. Komatsu is a highly respected cosmologist at the Max Planck Institute for Astrophysics.
His contribution here is brilliant. It bridges the gap between the 5% catalog and the 95% noise.
He utilizes the concept of cross-correlation. Since gravity dictates that matter will pool inside these dark matter halos, we know that massive bright galaxies do not exist in isolation.
They sit at the densest nodes of the cosmic web.
Exactly. The 1 million bright Lyman alpha emitters, the 5% of the data already cataloged by HUDX, they aren't discarded in this new map.
Far from it. They are the anchors.
The anchors.
In cosmology, we use a metric called the two-point correlation function.
Which means?
It essentially calculates the probability of finding a specific signal at a given distance from a known reference point.
Okay.
Komatsu's signpost method leverages this by cross-correlating the known 3D positions of the bright galaxies, the cities, with the heavily smoothed, faint-intensity map of the remaining 95% of the data, the suburbs.
So the supercomputer takes the coordinates of a known bright galaxy and says, based on the laws of gravity, there should be a localized overdensity of gas and dwarf galaxies right around this coordinate.
Right. It knows where to look.
It then looks at the intensity map for that specific region and extracts the faint signal that statistically correlates with the presence of that bright anchor.
The bright galaxies act as gravitational signposts shouting, "Look here, the cosmic web is thickest right around me."
By stacking the signals around hundreds of thousands of these signposts, something amazing happens with the math.
The random instrumental noise, which obviously does not correlate with the physical positions of the galaxies, averages out to zero.
But the real astrophysical signal from the intergalactic gas.
It constructively adds up. It stacks. This cross-correlation technique allowed the supercomputers to mathematically triangulate and reveal the three-dimensional morphology of the diffuse gas.
It's incredible to visualize the output. You begin with an empty void, punctuated by 1 million isolated, brilliant points of light.
A standard scatter plot.
Exactly, a scatter plot. But as the cross-correlation algorithm runs across the half petabyte of data, the spaces between those points begin to glow.
The massive filaments of hydrogen gas emerge from the background noise.
Stretching across millions of light years, linking the bright nodes together, the cosmic suburbs are illuminated.
It transforms our view of the 9 to 11 billion-year-old universe from a collection of isolated islands into a massive contiguous structure.
So what does this all mean? The empirical observation of this structure is a monumental achievement, obviously. But why does having this empirical map matter if we already had theoretical models?
That's a great question.
I mean, we have massive supercomputer simulations like Illustris TNG or the EGL project. These simulations take the initial conditions of the Big Bang, apply the laws of fluid dynamics, dark matter, gravity, and run it forward to see how the cosmic web forms. Aren't those simulations accurate enough?
Well, simulations are inherently limited by their resolution and by the assumptions encoded within their subgrid physics.
Subgrid physics.
In a cosmological simulation spanning hundreds of millions of light years, it is computationally impossible to model the physics of individual stars or individual supermassive black holes.
The scale is just too vast.
Right. Therefore, simulators use recipes to approximate the effects of supernova feedback or active galactic nucleus AGN feedback.
The processes that violently eject gas out of galaxies and back into the intergalactic medium.
Precisely. They have to estimate how much energy a black hole dumps into the surrounding gas because they can't simulate every photon.
And if the assumptions in those feedback recipes are slightly inaccurate,
then the resulting distribution of gas in the simulation will diverge from reality. Prior to the 8-Dex line intensity map, theorists could simulate the flow of gas into and out of galaxies at cosmic noon, but they lacked the comprehensive observational data to verify if their feedback models were actually correct.
The 8-Dex map provides the ground truth.
It is the real universe.
So cosmologists can now take the mock Lyman alpha emission catalogs generated by their simulations and directly cross-correlate them with the actual spatial distribution observed by 8-Dex.
It's the ultimate reality check for theoretical physics.
If your simulation says the gas should be blown 500,000 light years away from the galaxy by a quasar, but the HETDEX map shows the gas is tightly bound within 100,000 light years,
You know your subgrid physics recipe for AGN feedback is wrong.
it forces the theoretical models to conform to the empirical reality.
Exactly.
And honestly, this dynamic testing sophisticated models against raw, messy, real-world data is a critical philosophical anchor, not just in astrophysics, but in any data-driven field today.
Absolutely.
We live in an era heavily dependent on predictive models and algorithms. We simulate climate impacts, economic shifts, epidemiological spread. It is incredibly easy to trust the output of a model simply because its internal logic is sound.
But the ATX project reminds us that the model is merely a hypothesis.
Right. Until it is aggressively tested against the totality of the available data, not just the 5% that is bright, clean, and easy to measure.
That is a highly pertinent observation. The reliance on heavily filtered data to inform generalized models is a systemic vulnerability across all sciences.
The HETDEX map unequivocally demonstrates the value of mining the discarded data.
And within the context of astrophysics, this initial map is really merely the vanguard.
Just the beginning.
The successful application of line intensity mapping to Lyman alpha emission establishes a rigorous methodological foundation for the entire future of cosmic cartography.
Because the research team is already pivoting toward applying this technique to different spectral lines, right?
Yes, to map entirely different components of the galactic ecosystem.
Because the Lyman alpha line only tells us part of the story. It traces the ionized and excited neutral hydrogen.
It shows us where the massive hot stars are irradiating the surrounding gas.
It maps the active, violent regions of the cosmic web. But to understand the complete baryon cycle, how gas flows from the voids, cools, condenses, and eventually forms stars, we need to map the cold gas as well.
This raises an important question. How do we observe the reservoirs of fuel that haven't ignited yet?
The dark stuff.
Right. The immediate next step outlined by the researchers involves targeting the emission lines of carbon monoxide.
Specifically, the rotational transitions of the CO molecule.
While Lyman alpha traces gas at temperatures of roughly 10,000 Kelvin, carbon monoxide is an excellent proxy for locating giant molecular clouds.
Where the gas temperatures drop to just tens of degrees above absolute zero.
Freezing cold.
And those freezing, incredibly dense molecular clouds are the actual stellar nurseries. You need cold gas because thermal pressure fights against gravity.
Heat pushes out, gravity pulls in.
Right. Only when the gas cools down sufficiently can gravity take over, causing the cloud to collapse and ignite nuclear fusion to birth new stars.
Exactly. So by conducting line intensity mapping surveys for carbon monoxide, using millimeter wavelength arrays like LMA or future facilities,
And cross-correlating that data with the HTDEX Lyman alpha map.
astronomers can effectively trace the entire thermodynamic life cycle of galactic evolution.
You map the cold, infalling molecular gas with CO.
You map the regions of active massive star formation with the bright Lyman alpha peaks.
And you map the diffuse outflowing or heavily irradiated gas in the circumgalactic medium with the faint Lyman alpha intensity map.
Layering these maps over the exact same cosmological volume will give us a complete, multi-phase view of the universe at its most active epoch.
We will literally watch the respiratory system of the cosmos.
Galaxies inhaling cold molecular gas and exhaling hot, ionized plasma.
The technological capacity to do this is rapidly expanding too, with pioneering instruments like the Hobby-Eberly Telescope paving the way and upcoming line intensity mapping missions like SphereX and Exclaim coming online soon.
We are transitioning from an era of cataloging isolated objects to mapping the continuous fluid dynamics of the universe.
Julian Munoz correctly categorized this as entering a golden age for cosmic mapping.
It truly is. The HEDEX publication is a proof of concept that fundamentally validates the intensity mapping technique for optical and ultraviolet wavelengths on cosmological scales.
It proves that the faint, unresolved emission is not a barrier to observation, but rather a profound source of physical information.
Let's summarize the sheer scope of what we've discussed today.
We ventured 10 billion years into the past, to the cosmic noon, an era defined by extreme galactic assembly.
We examined how the quantum transition of the hydrogen atom produces the 121.6 nanometer Lyman alpha line.
And how cosmological redshift stretches that signal all the way into the optical band.
We detailed the massive engineering of the HTDX project.
The 30,000 fibers.
And the brilliant statistical pivot from point source cataloging to line intensity mapping.
By utilizing supercomputers to cross-correlate the known coordinates of 1 million bright galaxies with half a petabyte of highly smooth, previously discarded data, the team successfully illuminated the faint diffuse filaments of the cosmic web.
They transformed 95% background noise into the most robust empirical test of cosmological simulations ever created.
The transition from viewing the universe as a collection of discrete luminous points to a continuous, interconnected topological field, it's just an extraordinary scientific advancement.
It underscores a fundamental principle, really. The limits of our understanding are often dictated not by the absence of information, but by our methodological filters.
Wow.
We structured our most advanced cosmological models while ignoring 95% of the observational data because it failed to cross an arbitrary threshold of clarity.
Which demands that we ask a pretty profound question.
It does.
Yeah.
If the literal connective tissue of the universe was hiding in the noise we systematically discarded, what other foundational truths in physics, in the complex systems of our own planet, or even the structure of our societies are we completely missing simply because we have not yet developed the framework to find meaning in the blur?
The HEX map proves the information is there. The challenge is having the vision to read it.